A mobile unit substation, or MUS, is a substation that is secured to the frame of a trailer and transported by a tractor to various distribution stations across the province. They are installed in DSs to maintain service when the DS transformer is removed from service for scheduled maintenance, maintain service due to equipment failure, provide long or short-term load relief, or support capital construction projects. In very general terms, the MUS installation process involves using temporary connections to connect the primary side of the mobile to the primary side of the station, and the secondary side of the mobile to the secondary side of the station, and then switching the MUS into service to pick up the load of the DS. Unfortunately, no two MUSs are built the same, and no two DSs are built the same, which means that every MUS installation will vary. This training will explain the typical steps and requirements for installing the MUS. However, it will not cover every possible scenario. In the field, you will have to assess the components of the particular MUS and DS you are working with to determine a suitable installation sequence. When installing the MUS, you will be working in the proximity of energized equipment. It's important that everyone on site understands the job steps and the associated hazards, and that you take all necessary precautions to protect yourself and your coworkers. The following modules will be covered in this video: MUS components, distribution stations, job planning, receiving an MUS, rubber gloves, live line tools, and test equipment. Preparing a 115 kV MUS for installation. Preparing a 44 kV MUS for installation. Installing and removing a 115 kV MUS. Installing and removing a 44 kV MUS. Emergency installations. Shipping an MUS, and MUS annual maintenance. Hydro One currently has a fleet of 28 mobiles. These units have available primary voltages of 115 kilovolts, 44 kilovolts, and 27.6 kilovolts. Many of the 44 kV and 27.6 kV class mobiles are also capable of dual primary connections, including 22 kV or 13.8 kV. Due to the increasing distribution program, we are procuring new mobile units and refurbishing existing ones. Let's start by reviewing some basic MUS components. Every mobile is equipped with cables that are used to connect the low-voltage MUS supply. The basic makeup of a cable consists of the copper conductor, the conductor shield, the EPR rubber insulation, the insulation shield, the semicon, and the jacket. The cables are 4/0 copper with a capacity of 362 amps. The typical length is 150 feet. These cables are rolled up for transport on a cable reel with protective covers on each termination. The cable reel can be operated in either direction by a 120-volt motor. High-voltage cables. Typically, the high-voltage supply of the MUS is connected using bare copper conductor. However, some 44 kV mobiles have high-voltage cables that can be used for this purpose. They have the same basic makeup as the low-voltage cables, but they are 250 MCM and rated at 46 kV. The typical length is 50 feet. These cables are wrapped up and brought to site as required.
And then look back up at them.
However, some new mobiles are designed with a cable reel that will accommodate them. High-voltage cables can only be used on mobiles that are equipped with a designated support bracket. MUS transformers are oil-filled and have a capacity of anywhere from 5 to 20 MVA. They can be set to different primary and secondary voltages and must be able to match the voltages at the DS. For voltage regulation, MUS transformers are equipped with either off-circuit tap changers,
Good anytime you're done.
underload tap changers, tap links, or any combination of these. Some transformers use aluminum tanks to reduce the total weight of the unit. Cooling equipment. The MUS cooling system consists of fans, pumps, or a combination of the two. MUS transformers with a self-cooled rating are thermostatically controlled from a temperature gauge on the bank.
Record and reset all liquid and winding temperature drag hands on the MUS. Record in
The cooling for these units will operate automatically as temperature increases. Some MUS transformers do not have a self-cooled rating, which means the units must have the cooling equipment operating at all times while in service. If a mobile is equipped with reclosers, they will be VSO reclosers or Viper reclosers. The reclosers are used to pick up the load and protect the equipment in the event of a fault on the line. VSO reclosers open on all three phases when a fault occurs. They usually have a cycle of 1 quick trip operation followed by 3 slow trip operations. On the 4th operation, they will stay open if the fault isn't cleared. The close trip switch enables closing or tripping and is used to electrically test the operation of the recloser. The contact position indication is linked to the main operating shaft and is visible through the window on the cabinet. Closing the spring charge state indicator indicates whether the springs are charged or discharged. This is also visible through the window on the cabinet door. Closing springs are charged by a motor drive that provides energy to close the main contacts and simultaneously charge the opening springs. The opening springs are located in the recloser spring mechanism. This mechanism is supplied with an external trip pull ring that permits manual release of trip springs from beneath the cabinet by hand or with a hook stick. It is also equipped with an external close pull ring that permits manual release of closing springs from beneath the cabinet by hand or with a hook stick. Located within the recloser mech box are the F21 and F22 fuses. These are the supply fuses for the closing spring charging motor. Protection settings are set by installing different phase trip and ground trip resistors. These reclosers are also equipped with either a desensitizing relay or a doubler switch, which increases the MUS feeder protection should cold load pickup be required. G&W Viper reclosers. G&W Viper reclosers are currently being installed on new and refurbished mobiles. These reclosers are electronically controlled and equipped with vacuum tube interrupters. The normal operation is at 120 volts with a DC battery backup and a solenoid closing coil. Each phase of the recloser has 3 tripping solenoid coils that, when activated, will discharge a spring, allowing the recloser to open. These reclosers have 7 setting groups, which were programmed by P&C to accommodate the most common feeder protection requirements. There is also a Setting Group 8 option that is customizable in the event that Groups 1 to 7 do not meet the protection requirements. Field P&C must be contacted to program Setting Group 8. Mobiles without reclosers will be equipped with 9 low-voltage fuses, 3 for each feeder. These fuses provide feeder protection. The required fuse ratings can be determined using Appendix C in HOD's document SP 1609 and SP 1610. The fuse elements are configured on site while preparing the mobile for installation. Typically, 3 spare fuses are also prepared in case of an emergency situation. High-voltage fuses are installed on the MUS to protect the transformer from overloading. There are 3 high-voltage fuses on each unit, 1 for each phase.
Testing dates for high-voltage fuses, the make, model number, the procedures, and the numbers for selecting.
On 115 kV mobiles, the primary fuse rating is always 100 amps. The ratings are determined using Appendix C in HOD's document SP 1609 and SP 1610. On 44 kV mobiles or lower, the primary fuse ratings will vary. Surge arresters protect the transformer from any damage due to lightning strikes or overvoltage. There are 2 sets of surge arresters on every mobile. One set for the primary side and one set for the secondary side. Some surge arresters have multiple voltage level options and will need to be set to the same voltage level at the MUS transformer. This is done by connecting or disconnecting a shorting jumper. Every mobile is equipped with 1 high-voltage switch. This switch is used to isolate or energize the main transformer of the MUS. On some mobiles, the operating rods are dismantled and stored for transport. Mobiles without reclosers are equipped with single-phase stick-operated feeder switches. These switches are used to pick up the station load. Mobiles with reclosers are equipped with a low-voltage T-B gang-operated switch. This switch is used to isolate from the transformer to the low-voltage bus to allow for safe connection of the MUS cables. Mobiles with this configuration use the reclosers to pick up the station load. Some 44 kV units are equipped with a mast, which is a vertical metal pole that attaches to the primary side of the mobile. Various insulators are installed on the mast to get the high-voltage conductors from the switch to the DS primary stirrups. A mast is required at U70 stations if bare conductor is being used for the high-voltage connections. Due to the position of the mobile pole, the conductors need to be rotated around the mast in order to make the proper phase connections to the DS, while maintaining the necessary electrical clearances. If you are using 44 kV cables for the high-voltage connections, then you can roll the phases easily without the use of the mast.
Are you just going to do a close-up on the stick?
The mast is secured to the trailer horizontally for transport, and the mast insulators are stored on the mobile, either in bins or right on the frame of the mobile.
At Provincial Lines Technical Services, we do a lot of planning and specifying as far as power quality issues, load transfers, and connection impact assessments. We study all of the customer connection generators that are 500 kilowatts and below, and we also do DG impact studies that are generators that are 500 kilowatts and above that. Now, with the diagrams beside me, I'm going to be going over how we set protection and coordination with all the devices upstream and downstream from the TS. Starting with the diagrams beside me, I'm going to be going over protection from the 44 kV line, which is autonomy M28 44 kV, to Bensford Bridge DS. Now, starting with the transmission station, we have the 44 kV line. Now, at the relay of this M28, we have to make sure that this relay at the M28 is able to see its whole feeder end faults within less than 1.5 seconds for standard overcurrent protection. After we make our protection studies with the M28 44 kV, we have to coordinate this relay with all the downstream DSs from it. And as far as coordination is concerned, we have to coordinate the high side fuse at the DS with the TS relay. So starting at the distribution station, we have Bensford Bridge DS. Now we're going to have to model in this transformer into a program that is called TCC, Time Characteristic Curves. So the diagram beside me is showing the transformer modeled into this program. And this here is the inrush curve of the transformer. This is a 7.5 MVA transformer, and this last curve, the curve that we're concerned with, is this damage curve at the DS. And I'll show you in a moment exactly how we need to protect this transformer from faults downstream or upstream from this DS. So now that we have our transformer damage curve in, we are able to see from our GIS models that there's approximately 5,000 fault amps at this DS bus. So within these fault amps, we're going to have to distinguish what size of high side fusing, which is this line right here, this curve, in order to protect this transformer. So in this case, we're going to be using a 150 amp SMD1A standard type fuse that's going to protect this transformer from a fault of 5,000 amps. If there is a fault of 5,000 amps, this orange line is showing that this fuse will pop before the transformer damage occurs, clearing the fault and not having a transformer blow up. So this next diagram basically shows two sets of curves. One's going to be from a standard L-type recloser, and the other type is going to be from a Viper recloser. Now these Viper reclosers are becoming more popular within the DS stations, as well as being retrofitted excuse me, within the new MUS units as well. So as far as the comparison is concerned, this is a standard 200 amp hydraulic recloser, and this is a 400 amp Viper recloser. Now as you can see how the curves are almost upon each other, the hydraulic recloser is actually capable of double its pickup. So its frame coil rating is actually good for 400 amps, which is our Viper recloser setting as well. So basically, we'll basically design our Viper reclosers to be identical to an A1 B3 L-type recloser. So in the next diagram, we're basically going to show this 5,000 amp fault as well at the DS. We got our high side fuse, and now we got our recloser modeled in as well. So if there is a fault on the DS, this recloser is going to pick up this fault before the high side fuse even has a chance to see it, clear the fault hopefully, and if not, then this high side fuse will now clear the fault before the transformer damage occurs. So this next diagram here is basically showing a diagram of everything that we've modeled in so far, from the transformer to the high side fuse to the recloser settings. So everything needs to have its own order as far as coordination is concerned. The thing is as well, you can visually see that the recloser is going to clear the fault before the high side fuse, before transformer damage occurs. But these time differences are within milliseconds, and we do have standards as far as how many milliseconds before each device, because each device is going to require a certain amount of time to do its thing and trip and let the next device take care of it as well. So this next diagram is basically showing this recloser here, the DS station's 200 amp recloser, which is the L200A1B3, and this blue curve here is basically a downstream fuse that's going to be protecting a lateral or X amount of customers on our line. If there is a fault or a tree falls on that line that's downstream, this recloser has one fast shot that instantly closes in on the recloser, opens the circuit. Hopefully the fault is gone. If it's not gone, the customer's fuse will take the fault out, and the recloser will not trip, and it'll be just those 10 customers or 15 customers out of power, and not the entire F1 or F2 feeder. This last diagram here is basically showing how we choose a fuse for an MUS installation. So here we have the bypass fuse that's in purple, and the station's reclosers. So outside the station, there's approximately 1,000 to 2,000 fault amps, and we want this high side fuse to protect just the same way as the recloser did. Now, we're not going to be using the fast curve on the recloser. We basically want this fuse to protect everything up to its last delay curve on the recloser. So if there is a fault just outside the station between 1,000 to 2,000 fault amps, this high side fuse will protect the rest of the DS and clear that fault. So this was basically a way of showing how protection and coordination is done within Hydro One, and this is basically all done to ensure safety and reliability for our customers. So what we're looking at here is a standard L-type hydraulic 200 amp A1B3 recloser. Now you can see that there's 200 amps of continuous current that's allowable for this recloser, and also has a 400 amp maximum rating. So anything over 400 amps, it will trip on load or a fault. Now as far as the A1B3 is concerned, it's basically one fast curve and 3 delay curves. Now this first fast curve is basically if it's a storm happening and there's trees blowing, the tree branch falls on the line, the recloser will see this trip instantaneously, trip off and on once. That's when you get those lights in your house blink off and then back on again. And if they do come back on, then the fault is gone, the tree branch is gone, and everything's fine. Now if that tree branch is still there, the recloser will do its first fast trip. Fault is still there. Now we'll do 3 more delay curves, which is the B curve. So it takes a little bit more time, and it'll do that. It'll reclose in 3 times to see if that fault is still there or not. And if it is still there, then the recloser will trip and lock out, and that person will be out of power. So here's basically a full capture of the L-type recloser. As you can see, it's 200 amp, and it shows the curves on it, B13. You can get different type of reclosers with B22. This one is standard hydraulic 200 amp A1B3. So this here is a SMD standard 1A type fuse. This is a 125 amp rating. And down there at the very bottom where you see a standard speed TCC 153. So that TCC is the time characteristic curve that I was showing you in the diagrams earlier, and showing what type of curve this fuse will have on our system. Now the 125, every DS could be different. Some might have 150 amps, 125 amps. Some might even be 200 amps. Typically, the higher the fault amps at the DS, the higher the fuse rating we'll need to put in. So for 125, I mean, you could have maybe 3,000 fault amps at the DS, and a 200 amp fuse may have 5,000 amps, 5,000 fault amps at the DS. Hi all, these are the Viper reclosers that we were talking about earlier. How they're being retrofitted into the MUS mobile units as well as the distribution stations. Here's just a good shot of these reclosers. Now, a few things that are really good with these reclosers, as opposed to the typical L type, are the interrupting rating of these are 12,500, as opposed to the typical L type, which are 4,000 amps. Now, these also have a lot higher rating, 800 amps. And as far as selecting the curves, they're a lot more versatile as far as choosing what to pick as far as coordination downstream. So here's another shot of the tag that's on the recloser itself. You can see that there's the 800 continuous amps that are allowable on this recloser, as well as the interrupting current of 12,500 amps. So over here is just a shot of the 651R controller that controls the Viper reclosers. Now, I'm not going to get into too much detail about it. As far as the auxiliary buttons that are on this controller, we're able to actually set 6 different setting files per recloser. Now, this is what comes in really handy about these mobile units, is we could have different setting files for each setting group. So as far as going to a station with high fault amps, low fault amps, long or short feeder ends, we're able to switch this with the switch of a button, and have our reclosers now see its feeder end in less than 3 seconds. So this makes it very versatile and very easy to manipulate as far as moving from station to station.
The MUS installation procedure will vary depending on the station type. The most common distribution station types include lattice structure stations, U70 stations, U90 stations, U12 stations, integrated modular stations, and acquired municipal electrical utility stations. Most distribution stations are designed to accept primary and secondary station voltage taps from the MUS in various configurations to bypass and de-energize key station equipment such as transformers, low-voltage bus, and feeder reclosers. Due to the limitations of the varying station types and layouts, there are differences in how each station type includes the high-voltage and low-voltage taps for the MUS. A lattice structure station, also known as an Item 27 or Jones-style station, typically has the station ingress overhead on air-insulated strain bus from the MUS pole. The station egress is typically an air-insulated strain bus that is supported by an H-frame. The egress is then tapped to the lines outside the station. The MUS directly connects to the station ingress at the MUS pole and the station egress, bypassing the transformer, low-voltage bus, and reclosers. The neutral bushing on the MUS is also connected to the distribution system neutral at the overhead egress exiting the station. A U70 station, sometimes referred to as a low-profile station, is built lower to the ground for aesthetic reasons. The supply voltage can enter the station either overhead or underground. The feeder supply exits the station underground and connects outside the station on pole structures equipped with dip switches. These stations are equipped with a T-B switch that isolates the transformer from the low-voltage bus. The MUS high-voltage connection taps into the high-voltage termination and mobile connection structure. The MUS low-voltage connection typically taps into the low-voltage bus supplying the outgoing feeders that form the station egress. The MUS in this case isolates and allows de-energizing of the station transformer, but not the low-voltage bus. If you are using copper conductor for the high voltage connections, a mast will be required to make the proper phasing connections. However, U70 stations built in the last 10 years will have an item 905 exit structure, in which case you can also isolate the entire DS, and a mast is not required. If the station does not have a low-voltage exit structure and you require the low-voltage bus to be de-energized while the MUS is in service, a transition pole will need to be erected. The distribution system neutral is brought into a U70 station either on a neutral bus bar or is directly bonded to the ground grid. The neutral from the MUS should be connected to this system neutral. If you require the use of the electronic reclosers on the low-voltage bus while the MUS is in service, then you need to ensure that the station service is connected to the bus side of the T-B switch. If the tap for the station service is on the transformer side of the T-B, then the reclosers will need to be energized by an external supply. A U90 station is also built lower to the ground. The supply voltage can enter the station overhead or underground, and the feeder supply exits the station underground. This type of station is always equipped with an item 905 exit structure. When the MUS is installed at a U90 station, the MUS feeder cables are connected to the stirrups on the exit structure, and the MUS high-voltage conductors are connected to the stirrups on the MUS pole. The neutral from the MUS is connected to the station neutral on a bus bar. The transformer and low-voltage bus are isolated by disconnecting the loops on the exit structure. At a U12 station, also referred to as a pad mount station, most of the station equipment is sitting on a concrete foundation. This includes the transformer, the switchgear that accepts the low-voltage cables from the transformer, the reclosers, and the station service transformer. Everything is connected with underground cables. The supply voltage enters the station overhead and then connects to an underground to overhead transition pole. This pole is equipped with a disconnect switch, fuse, arrestor, and cables connected to the primary side of the transformer. The feeder supply exits the station underground. When installing the MUS at a U12 station, the MUS high-voltage conductors are connected to the transition pole. The MUS feeder cables are connected to the item 905 exit structure. The neutral from the MUS is connected to the station neutral on a bus bar. Everything in between the transition pole and the exit structure is isolated. Integrated modular distribution stations and acquired municipal electrical utility stations were never designed to accommodate the installation of the MUS. If installation is required at either of these station types, engineering services and maintenance technical services must be contacted. As you all know, the planning and preparation stage is an important part of any job we do. In planned circumstances, job planning for an MUS installation should begin well before the MUS arrives at the DS, and of course continue throughout the duration of the job. There are several tasks that must be done to prepare for the installation of the MUS. This includes planning for metering, reviewing the appropriate documentation, inspecting the DS, contacting the controlling authority, preparing a job planning folder, and conducting a tailboard. When the MUS is installed at a DS, it will often bypass the existing station metering. If it does, an alternative method of metering is required while the MUS is in service in order to prevent loss of revenue and remain compliant with the IESO. An electronic recording ammeter, or ERA, is a portable device that is used to temporarily monitor feeder line currents while the DS is out of service. They are hung on conductors and record the current for 5, 15, or 60-minute intervals, depending on the device setting. This data is stored in the device's memory and downloaded by provincial lines on a weekly basis. Any station listed on the Revenue Metered Distribution Stations list requires ERAs. This list is linked in HODS documents SP 1609 and SP 1610. In planned circumstances, ERAs must be installed the day the MUS is put into service. Provincial line zone scheduling and the metering service provider or MSP department must be notified well in advance of the date the MUS is being installed so they can plan accordingly. They must also be notified of the time and date of removal. When NOD is the controlling authority, ERA requirements must also be discussed with OGCC's Operating Planning Department and documented in the NOMS request. In emergency situations, ERAs must be installed as soon as possible within 2 business days. In these circumstances, ensure that provincial lines and MSP are notified as soon as possible with information on when the MUS installation will take place or has taken place, the need for ERAs, and the duration expected. MUS 40 is equipped with permanent revenue metering. When installing this mobile at a station requiring metering, contact local P&C field services. They will coordinate registration with IESO. In emergency situations, contact P&C within 2 business days after placing the MUS into service. Review the MUS operating diagram, station operating diagram, and the MUS manufacturer's instructions to become familiar with the MUS being installed, and develop a plan for switching it in and out of service. Each MUS has unique nomenclature for its various components. This will be outlined on the MUS operating diagram. You must also physically inspect the DS to confirm the availability and integrity of all required equipment and material. Check that the proper high voltage and low voltage MUS connection points, or stirrups, are installed. If they aren't, you must arrange for provincial lines to install the stirrups before the MUS goes into service. Stirrups can be ordered using the MM numbers found in SP 1609 and SP 1610. If the station has more feeders than feeder positions on the mobile, then you must arrange for provincial lines to tie the 2 lightest loaded feeders together external to the DS. Ensure that the total anticipated load on each MUS feeder will not exceed 360 amps per phase. Check the switch type on the DS feeders. MUS cables cannot be hung on energized feeders in the same span with solid blade inline disconnect switches unless they are approved AMPAC switches or have been retrofitted. This is due to mechanical failure of these switches causing energized conductors to fall to the ground. This is an approved AMPAC ILDS. A retrofit ILDS will have a 15 kV polymeric suspension insulator installed at each end of the switch. Non-retrofit switches must be replaced by provincial lines before installing the MUS. If this is not possible, you must inspect switches from an aerial device for pitting, cracked ferrules, signs of arcing, or pin discoloration. If no abnormalities are found, isolate the feeders to hang the cables. The preferred isolating device is an MSO. Ensure there are no missing or broken grounds or neutrals. Pay particular attention to the neutral connection between the transformer bushing and system neutral, as this can sometimes be compromised due to copper theft. Also, check the location of the ground connection. If a ground connection and a line neutral connection are made at the neutral bushing, then you must permanently bond the two conductors together using thermionic or approved copper compression type connectors. This must be completed before removing the neutral or ground connection on the XO bushing. If this is not done, the ground to neutral connection may be compromised. Inspect the station for any obvious signs of defect, such as cracks, chips, or tracking on insulators, bushings, and surge arresters. Damage on potheads and cable terminations. Signs of arcing. Failure of the MSO assemblies. Fuses not seated or latched correctly. Insulator cap separation on the fuse jaw of the S&C fuse combo switch, or the grub screw improperly secured on the 44 kV switch drive pipe on the T-L. Check for severe cracks or rot on the first wood pole structure within the station, as well as the first wood pole outside of the station. These poles must be able to support the added weight and stress of the low-voltage cables. A good indication of a bad pole is if the top end has deteriorated due to age and weather. You can also tap the pole with a hammer to listen for hollows or voids. If you find severe rot or damage, stop the job and contact provincial lines to inspect the poles and replace them if required. Contact the controlling authority. The controlling authority for DS work will be provincial lines or the OGCC. They must be notified prior to work commencing of the scope, location, and duration of work. You must also provide them with a reliable means of communication, which is generally the cell phone number of the UTS or designated person in charge. Prepare a job planning folder. Before the MUS arrives, the UTS or a designated person can begin filling out a job planning folder with information such as the job description, job steps, known hazards, etc. This folder should be completed, updated as required, and signed by the crew on site each day MUS work takes place. And of course, a tailboard meeting must be conducted on-site immediately prior to beginning any work. Several tailboard discussions will likely occur when installing the MUS, due to the number and variety of job steps required. If any changes occur, remember to stop and discuss with the entire crew.
My main concern today, mind on task, proper communication with coworkers. When we're going to be installing those 44 kV lines, we're going to have a designated spotter. And obviously FRC and PPE.
The MUS will be transported to the DS by a tractor equipped with air suspension. Arrangements such as date and time of arrival must be coordinated with the tractor driver. Before the MUS arrives, complete a site visit to determine the proper location to land the MUS. The location must allow for proper high-voltage phasing connections and low-voltage feeder connections, limits of approach adherence, proper clearance for required work on the DS equipment, necessary grounding connections, 2.5 meters on either side of the high voltage end of the MUS to permit extensions of the two outside phases, and a minimum of 3 meters between the MUS and the station perimeter fence. If you can't maintain a clearance of 3 meters between the MUS and the fence, then ground the MUS to the station ground grid and provide a temporary bond between the MUS trailer and the station fence ground while working and switching. Ensure that all personnel, members of the public, and equipment are clear of the fence. Once the MUS is in service, remove the temporary bond between the trailer and the fence. On 115 kV mobiles, if the fence is located on the red phase side of the MUS, an additional 1.5 meters is required between the fence and the mobile because the red phase on the high voltage fuse swings outward. This means a total required clearance of 4.5 meters. The MUS should also be parked as far back as possible, leaving gate access to the station for trucks, cranes, floats, and other required equipment. However, in some stations, the location of the mobile pole forces the MUS to block gate access to the station. In this case, any additional equipment that needs to be inside the station must be brought in before the MUS arrives. Remove any garbage, debris, or material from the selected area. Use the MOT Book 7 Temporary Conditions Field Edition to prepare a traffic control plan if required. When the MUS arrives, it is backed into position using a spotter to ensure that there is enough clearance between the gates and the trailer. Once it is safely backed off the traveled portion of the roadway, the driver and the RME should have a discussion about the final placement of the MUS. Using hand signals, direct the driver to position the mobile in its final operating position. Sometimes multiple attempts may be required. Level the MUS using hardwood planks, only if it is 5 degrees out of level side to side or front to back. This is generally determined by eye, but some mobiles are equipped with leveling gauges. Most of our stations are graded well within 5 degrees, so leveling is rarely required. Some consideration should be given to the local weather conditions, such as wet soil or frost in the ground that may disappear while the unit is in service. Never use the landing gear for leveling. It is only to be used to provide stability. Our mobiles are equipped with either manual landing gear or automatic landing gear. The manual is more difficult to operate than the automatic, and in the past there have been several incidents involving this type of equipment. When landing an MUS equipped with manual gear, it's important to follow the proper sequence of operation in order to prevent potential injuries and damage to the equipment. The proper method of deploying the landing gear is posted at each crank handle on the MUS. There are two possible configurations for manual landing gear on our mobiles. One crank handle that operates one set of landing gear, or one crank handle for each leg. In either configuration, it's critical to follow the posted instructions. When the MUS is ready to be landed, the driver will begin by fully inflating the suspension airbags to lift the trailer up. You can then remove the landing pads from the shipping compartment and place them under the landing gear legs. Once the airbags are fully inflated and the MUS is at its maximum height, the landing gear must be lowered to the wooden landing pads using the crank handles. Before operating the handle, inspect it to ensure there is a spring latch mechanism and the ferrules are welded to the handle or removed. Ensure personnel and equipment are clear of landing gear when it is extended or retracted. Pull the handle out for high gear and turn it clockwise to lower the rear landing gear legs until they touch the landing pads. Then do the same with the front legs. Make sure to position yourself clear of any inadvertent movement of the handle while doing this. Once all landing gear legs are lowered, push the crank handle in for low gear and make an additional 5 to 6 turns. This will take some of the weight of the MUS off the tractor. Do not switch between high and low gear while rotating the crank handle.
It's important that when you're dropping the MUS that you put the landing gear all the ways down to the pad in high gear until it touches, and then give it 5 or 6 cranks in low gear till you hear the air coming out of the truck. It's releasing pressure off the suspension system, because what happens is when we come to pick the MUS up, if we don't do that, the MUS is sitting too low, we can't get hooked up to it. So then we mainly have to crank the MUS up in the air, which is where, with the weight of the unit on these outriggers, this is where people run into problems with the gears breaking and the handles coming back and hitting them in the face and body parts.
After the legs are lowered, stow the handle in low gear to prevent movement due to load shift. The driver will then place the automatic air ride control to manual and release the air from the MUS airbags. Once all the air has been released from the suspension, the weight of the MUS is supported by the landing gear. The driver will then release the fifth wheel. Disconnect the air lines and electrical connections and uncouple the tractor. The MUS is now in its final operating position.
We'll take a couple moments to discuss the Holland landing gear on MUS substations. In the past, several injuries have occurred around this particular device. As you can see, we got several warning plates here and a procedure for landing and moving the mobile. These landing gear devices, the mechanism of injury to an employee would be because of stored energy within the mechanism and the employee's hand potentially slipping off and the handle returning and striking an employee on their upper body. These ferrules have been modified as a result of that incident, and they've been spot welded so they don't come off. There's another mechanism of failure which allows this handle to knuckle over if this spring and bolt mechanism isn't in the proper position, and allows the handle to slip out and fold, thereby the employee losing a grasp on this handle, and once again the stored energy brings the handle around for an upper body strike. This modification here has been made to all of our MUS crank handles, and what it does is it prevents the handle from inadvertently releasing while the operator is lowering or raising the landing gear. And the way it works is a little spring pushes this tab into a slot in the handle, which prevents the handle from moving backwards while the crank handle is being rotated. There's been mechanical failures inside where the shaft separates, allowing the employee's weight distribution to change and fall either forward or backwards depending on whether they're lowering or raising the device. These particular landing gear, the specifications far exceed the weight of the actual mobile unit substation. But where we run into problems is when the landing procedure is not followed and the landing gear itself becomes damaged. And when we have distortions in the vertical components here, or we bend, or this gets bent forwards or backwards, you have a significant drag within the mechanism which allows it to store the energy. And this is a result of the mobile being landed improperly, brakes being released or in the wrong sequence, and then the weight of the machine pushes forward and bends it. As you can see, this has been repaired already because of that type of damage. Yeah, this bar has been added to prevent the landing gear from coming out of alignment in reverse. That's a common form of damage. When the airbags are released, the unit itself will move forward and put backwards pressure on the gear.
For MUSs with hydraulic operating gear, the landing gear is lowered using the hydraulic power supply motor and then secured with locking pins. The full procedure is included in SP 1611, and instructions are also posted on the mobile. It is an easier and safer method. Once the tractor has left site, ground the MUS to the station ground using a temporary portable ground. Open the transformer cooler oil valves and breathers. Some mobiles will also be equipped with a 1-inch equalizer valve that needs to be closed. Ensure that the internal-external supply switch is in the external position. Check that the isolating disconnect switch is in the open position if equipped. Connect the MUS to a 120-volt 20-amp external power source and fill out the receiver columns of the shipping checklist found in the MUS shipping and service binder. At this point, all receiving tasks have been completed. If required, the MUS can be left like this until the crew is ready to put it in service. Before we look at the installation practices, it's important that you have an understanding of the live line tools you will be required to use throughout the job. Rubber gloves must be worn when handling energized MUS cables. This provides a barrier against induction on the cable or electrical contact should the cable insulation fail. They should also be worn when operating manually operated switches and in damp or inclement weather conditions when operating live line sticks. Most rubber gloves are bicolored with a black rubber outer surface and either a yellow or red interior surface and cuff. The two-color fabrication of these gloves lets you easily identify points of wear or other defects in the outer black surface when the glove is inflated during inspection and air test. Rubber gloves are always worn with protective covers. These covers consist of a leather glove combined with a cuff of synthetic or leather material. This cuff is for mechanical protection only and is not to be relied on for electrical protection. When covers are on the gloves, the rubber glove cuff must be visible above the glove cover for the prescribed amount according to the class of gloves. The rule of thumb is 1 inch of glove showing above the cover per 10 kV of test voltage and ½ an inch for any glove tested below 10 kV. A thorough inspection of selected gloves must be performed prior to use. Check the manufacturer's stamp that appears on the cuff of each glove for the class and maximum voltage rating. The glove should be Class 2, which means it has an industry rating of 17,000 volts phase to phase. However, the Hydro 1 rating for Class 2 gloves is 15,000 volts phase to phase. Most rubber gloves are similar in construction, so the manufacturer's stamp is the only way to confirm the class. Check the testing lab stamp for the Do Not Use After date. Rubber gloves must be retested at a certified lab at least every 90 days and are never to be used beyond their expiry date. Perform a visual test and an air test. A visual test tells you if there is excessive wear. Stretch the glove to look for cracks and tears. Reverse the glove and do the same on the other side. Check between all fingers. Look for punctures, hard spots, foreign material, or breaks in the surface. With the two colors, these abnormalities are usually easy to see. Check the glove cover for any wood or metal splinters that could puncture the rubber gloves. If the covers are oil or penetrox soaked or worn through in spots, they should be replaced. A cut through the leather or synthetic part of a glove cover should be investigated to see if any damage has been transferred to the rubber glove inside the cover. Minor cuts and abrasions to the outer black surface of the glove are permitted if the contrasting inner color does not show through. The inner yellow or red part of the glove represents 80% of the glove thickness. It is not possible to determine in the field just how deep a cut or abrasion may be. Therefore, any break on the inside of the rubber glove renders the glove defective. It must be returned to the work location for replacement. An air test tells you if there is a puncture. Twirl the glove to fill it with air and trap it by rolling up the glove cuff. With your free hand, squeeze the glove in various places. This inflation of the glove will amplify any small damaged spots that might not be found by ordinary visual inspection. While the glove is inflated, hold it up to your face to feel or hear if any air is leaking through a puncture. Do not wear rings or watches under your rubber gloves. Electrical research has shown that many gloves have indications of corona cutting where these items contact the gloves. Live line sticks are made of fiberglass reinforced plastic tubing with a unicellular foam core. The fiberglass tube structure gives them great strength with light weight. The foam core keeps them clean and moisture-free inside. MUS work requires the use of grip-all sticks and sectional sticks. Grip-all sticks operate live line clamps and are used to install and remove portable grounds, hang and remove work protection tags, hang and remove cables, or open and close switches, MSOs, or -LC and -BC jumpers. They come in different lengths, but the main sizes used for MUS work are 6 feet, 8 feet, 10 feet, or 12 feet. A sectional P2 switch stick is equipped with a permanent top and bottom fitting. These fittings allow sectional sticks to be connected to one another to extend the total stick length if increased reach or work clearances are required. The fitting at the top of the stick supports various interchangeable heads. The most common head for a sectional stick is a P2 head. This head allows opening and closing of any hook stick-operated switch. When installing an MUS, you may use a sectional stick equipped with a P2 head to open and close reclosers, hang and remove tags, open and close low-voltage fuses, or operate single-blade or phase switches. Before using a live line stick, check the Kinetrix test sticker for the Do Not Use After date. Look for chips and signs of tracking or damage on the fiberglass shaft. Breaks in the surface, exposing fibers to possible moisture, mean the tool is unsafe for use and must be sent for repairs and retesting. Check the operating end for cracks. Pay special attention to the fittings. Any sign of cracking of the finish at the point of attachment means the tool has been overstressed and should not be used. Check metal components for signs of excessive wear, deformation, or cracks. Inspect epoxy and fasteners used to bond hardware to the fiberglass. Check the mechanical function to ensure the stick operates smoothly and the latches fasten properly. Check that the switch stick hook has free movement and will retract fully into the stick as required. Lubricate moving metal parts of live line tools as required with approved dry film lubricant. If the stick is dirty, wipe it down with isopropanol. Live line tools must have an unbroken length of fiberglass insulation equal to or greater than the absolute limit of approach for the voltage being worked on. Ensure that the stick you select is the proper length to allow for the required limits of approach. Do not encroach on these limits by choking too far up on the stick. Remember that the top metal portion of the stick is not considered insulated, so measurements must begin after this point. Chance phasing sticks are the recommended tool for performing phase checks. Each testing unit consists of 2 insulated fiberglass sticks with end fittings threaded for interchangeable probes. The probe fittings couple with a high-impedance component encased in each stick. To complete the test circuit, a 22-foot length of insulated flexible cable is stored on the reel attached to one stick and connects to the voltmeter on the other stick. These phasing sticks can only be used on lines up to 36 kV. The cable insulation is limited to 15 kV for lightweight and ease of handling. Ensure that the testing unit has two labels, the orange ESA-approved label and the white Certified Lab Yearly Recertification label. The ESA label will be on the main stick head. The Yearly Inspection sticker will be on both sticks. Inspect the stick for damage and ensure the handle portion of the stick is clean and dry. In order to maintain proper working clearances, each phasing stick must be connected to a P2 stick via the universal spline built into the plastic casing. You can also connect the phasing sticks to a grip awl, but this requires a special adapter. Working clearances must be maintained below the connection point. Only the length of the connecting cable necessary to permit the contacts to reach between the points of measurement should be used. Any remaining cable length should be kept wound on the reel. Keep the connecting cable as far as possible from the subject conductors, other conductors, and grounded or metal structures and platforms to avoid influence that may distort meter indications. The phasing stick should only be left on an energized line long enough to obtain a reading. Ammeters are used to check the current on live lines. When installing the MUS, you will need to check current on the MUS feeder cables and the DS feeder lines. When overhead lines require testing, you must clip the ammeter to the top of a live line stick, which allows you to raise the ammeter to the desired height and maintain proper working clearances. An LIV is a line isolation verification device. It is a portable, small, lightweight instrument that detects the electric field on overhead or underground distribution and transmission lines in the range of 200 volts to 550 kilovolts. The function of this device is to verify if a line is isolated and safe to ground. An LIV is also used in conjunction with a live line stick. The device gives an audible and visible signal when the voltage on the line under test exceeds 50% of the line's nominal voltage. Any induced voltages will usually be well below 50% of nominal. Potential indicators must be retested annually. Before use, check the Do Not Use After sticker date and test it on a known source. Refer to the station's Approved Test Equipment list for up-to-date information on approved test equipment. This list is found on the Test Instrumentation Committee website. Keep tools dry and free from dirt and dust using a clean cloth and isopropanol. When in use, they may be placed on racks or leaned against a fence. If the tools are laid flat, a clean, dry tarpaulin must be spread out to prevent the tools coming in contact with the ground. If tools have to be used or left out in inclement weather, they must be dried as soon as possible and checked for any signs of tracking. Any indication of this makes the tool unsafe for use, and it must be submitted for inspection before being placed back in service. Make sure all tools are securely fastened in their proper location when being transported. The hardware should not make contact with other tools. When possible, live line sticks should be stored in their protective bags. If the finish on a stick is broken, enough to expose the fibers of the fiberglass reinforced plastic, it must be shipped to Kinetrix Inc. No alterations to the tools should be made in the field. Before beginning the prepping activities, conduct a tailboard to discuss the job steps and associated hazards. While working in the high-voltage switch structure, care must be taken due to obstructions, small footing areas, and uneven or potentially wet and slippery working surfaces. Proper fall protection must be used above 10 feet. Let's take a look at the prep work required for MUS 29, which is a 115 kV unit. Remember that these steps can vary based on the MUS and the DS you are working with. Not every 115 kV unit will have the equipment we are about to discuss. Conditions such as stations with no 115 kV MUS connection structure or other non-standard configurations will alter the required permits. Remove the shipping covers on the high-voltage and low-voltage transformer bushings, surge arresters, and gauges. Once all the covers have been removed and stored, visually inspect insulators, surge arresters, and bushings for signs of damage or defect. If required, clean them with isopropanol. First, remove the shipping rods. Loosen the turnbuckles and remove the pins. Then remove the rod, reinstall the pins in their proper position, and lower the rod to the ground. Untie the high-voltage switch blades. Unbolt the top braces and lower them to the ground. Each brace is secured by 4 bolts. Remove the lower shipping brace, which is pinned and secured in 3 places, and lower it to the ground. Remove the high-voltage fuse jaws from the shipping position and install them on the adjacent high-voltage insulator. Remember to install the jumper between the base of the high-voltage fuse and the high-voltage switch on all 3 phases. Remove the high-voltage fuses from the storage cabinet and place them on a work surface for inspection. Ensure that the fuse has a valid air test label. The fuse airflow test is valid for 5 years. Check the make, model, and style of the fuse, the rating of the fuse, and the standard speed curves. Check the contacts and springs for damage, heating, or binding. Before installing the fuses, inspect the fuse exhaust port for obstructions or contamination. And test for continuity using a digital multimeter. Once you have inspected and tested the fuse, raise it into position and place it in the jaws. This may require some finessing. Ensure all fuses are latched securely in the closed position. Expand the HV switch into its operational position. Remove the 9 transportation bolts to allow for expansion of the high voltage switch. Carefully roll out the switch. Install 3 locking bolts into the anchoring plate to hold the structure in the extended position. Then do the same for the opposite side. Install the operating handle. Remove the operating arms from their storage position. Install the arms, starting with the red phase, wishbone end first. Then the white phase, which will have 2 interphase connecting rods. Ensure that both white ends meet up on the center paddle. Then proceed to the blue phase, where you can use the switch operating handle to align your final pin with the center paddle. The operating rod ends are color-coded to make installation easier and maintain switch alignment. Finally, install the arcing horns on all 3 phases. After installing the driving mechanism, open up the switch with the hand crank to ensure that there is no binding on the mechanism drive and that the switch is operating freely. Install the high voltage switch grounding mat, connecting the ground lead to the MUS ground bar. Switching mats should not be installed during erection of the mobile because it creates a tripping hazard. While standing on the ground mat, test operate the switch closed, checking that all 3 phases touch the respective arcing horns at the same time before settling into the jaws. The main moving contact should be centered when entering the main contact jaw. The moving contact should turn and compress the main contacts. All moving contacts should be within 5 degrees of horizontal. Use some isopropanol and an abrasive wipe to remove any contact contamination. Then apply a light film of convoy contact grease. Inspect the contacts for any damage or missing parts. Then operate the switch to the fully opened position and check that all 3 phases are leaning back. Lock the operating handle in the open position. Install the portable ground mat at the MUS T-B. While standing on the mat, test operate the switch. Check that the switch operates smoothly, the jaws line up, and the arcing horns touch before the main contacts are made. Clean and grease the contacts if required, and then lock the operating handle in the open position. Open the outer and inner doors of the F1 and F2 control cabinets and check that the various controls are set correctly. For the number of operation selectors, the ground trip socket should be set to 1. This is the number of fast ground trip operations. The lockout should be set to 4. This is the number of operations to lockout. The phase trip socket should be set to 1. This is the number of fast phase trip operations. The reclosing interval delay should be set as follows. First, to 0.5 seconds. Second, to 2.0 seconds. And third, to 2.0 seconds. The reset delay plug should be set to 10 seconds. This is a solid-state component easily changed to any of the 8 delay values. The non-reclosing normal reclosing switch should be on non-reclosing. This sets the control for a one-shot lockout without disturbing the lockout setting of the operation selector. The ground trip blocking switch should be in the normal position. And the local remote switch should be in the local position. Reset the A, B, and C ground fault target indicator. This device records whether a phase or a ground fault caused the recloser to operate. Check the battery charging rate in both F1 and F2 recloser cabinets using the recloser battery charger ammeter located on the face of the control cabinet. Press the switch and take a reading. The ampere reading should be between 9 and 30 milliamps. If it's less than 9 milliamps, the battery charger board is not supplying sufficient charging current to the battery, and the board must be replaced. Using Appendix C in SP 1610, select and install the appropriate phase trip and ground trip resistors to protect the low-voltage feeder circuits. These resistors will be found in the storage box on board the MUS. The minimum trip resistors establish the minimum trip current for the ground and each phase. Using the lamp test and lockout test switch, verify the green lockout test light illuminates. The lockout indicator signal lamp provides visual indication of lockout when the switch is operated. The lamp test lockout indicating switch indicates lockout and tests the indicating lamp. Verify electrical operation of the reclosers. Testing the 86 relay requires both reclosers in the closed position with the springs charged. Manually reset the relay and immediately place the recloser local remote switch in the remote position. After a small time delay of approximately 10 to 20 seconds, both reclosers should trip open. The 86 relay will trip the reclosers to protect the transformer in the event of loss of cooling. The timing delay prevents the 86 relay from tripping the mobile in the event of a reclose operation on the 115 kV circuit. Once the test is complete, place the local remote switch back to the local position. Verify the settings on the desensitizing relays located in the recloser control cabinet. The 27D relay setting should be placed at 30 minutes. The T relay setting should be placed at 45 minutes. These settings provide cold load pickup ability, allowing the reclosers to carry double the resistor settings for a set period of time. Record all liquid and winding temperatures on the MUS record. Then reset the temperature drag hands. Check the current tap positions of the station transformer. This station's OCTC is set on tap 1. The ULTC is set on tap 8. Refer to the DS transformer nameplate to determine what voltage the station transformer is set to based on the current tap positions and record the voltage levels. Here we have a primary voltage of 121,276 volts and a secondary voltage of 13,233 volts. Check the MUS nameplate data to determine which positions the offload taps, links, or series parallel switches need to be set to match the secondary voltage of the station. The voltage on this particular mobile will be adjusted using 4 offload taps. In this case, we need a secondary voltage of 13,233 volts, which this mobile does not offer. The closest options are 13,800 volts or 12,470 volts. This means you need to first calculate the station transformer ratio and then calculate the MUS transformer ratio for both the 13,800 volt option and the 12,470 volt option. The MUS offload tap should be set to whichever voltage option has a calculated ratio closest to the station transformer calculated ratio. This will ensure the greatest range of operation on the ULTC. Because this station has a delta star transformer, the phase to neutral voltage is root 3, 1.732 of the phase to phase voltage, which equals 7,640 volts. That's 13,233 divided by 1.732 equals 7,640. Take the high voltage reading, 121,276 volts, and divide it by the low voltage reading, 7,640 volts, to get the calculated station transformer ratio. 121,276 divided by 7,640 equals 15.87. 15.87 is the station transformer's turn-to-turn ratio. To determine the MUS transformer ratio, you must first calculate root 3 of your voltage selection options. Root 3 of 13,800 is 7,967. 13,800 divided by 1.732 equals 7,967. And root 3 of 12,470 is 7,200. 12,470 divided by 1.732 equals 7,200. Use the neutral position, 115,000 volts, of the high voltage ULTC to determine the MUS calculated ratio. The 13,800 volt option provides a ratio of 14.43. 115,000 divided by 7,967 equals 14.43. The 12,470 volt option provides a ratio of 15.97. 115,000 divided by 7,200 equals 15.97. Since the station transformer ratio is 15.87, The 12,470 volt option is the best setting to ensure the greatest range of operation on the ULTC. Refer to the MUS nameplate data to determine what position the 4 MUS offload taps need to be set to for 12,470 volts. For this specific unit, the OCTC is operated by releasing the centering pin, rotating the handle, and repositioning the centering pin into the locked position. The final ULTC tap position will be selected to match the operating conditions when paralleling the MUS and DS. Some metering units and bus PTs may have a non-standard ratio. This will also require calculation and further consideration on your TCX relay output. Some units are equipped with an auxiliary transformer switch. The output of the auxiliary transformer is proportional to the secondary voltage of the MUS transformer, so this switch needs to be set to half or full depending on the selected MUS secondary voltage. Transformer ratio tests should be completed after the MUS off-circuit taps have been placed in the required operating positions. Connect the ratiometer ground lead to the ground stud. Connect the high voltage and low voltage ratiometer test leads to the test instrument. Then connect the test instrument to an appropriate power supply. Take ratio readings with the tap at neutral, one above and one below neutral, and the highest and lowest tap positions. A final ratio reading should be taken on the tap position that will likely be used while paralleling the MUS to the DS. Record your results on the MUS record and compare to the previous results. After the ratio test is complete, remove the high voltage ratiometer leads from all 3 bushings and remove the low voltage ratiometer leads, including the XO lead. The XO lead must be reconnected to the XO bushing after all diagnostic testing on the MUS has been completed. Expose and disconnect core ground connectors from the main transformer core and the auxiliary transformer core. Use a digital multimeter to check the core grounds resistors. Test core grounds at 1000 volts for 1 minute. Measure and record the core ground resistance and record the transformer ambient temperature. Any reading of less than 100 megaohms must be reported to Maintenance Technical Services. For a 2-winding transformer, you must test high voltage and low voltage windings to ground, low voltage windings to grounded high voltage windings, and high voltage windings to grounded low voltage windings. Each test is performed at 1000 volts for 1 minute using a Megger tester. If you are using an electronic Megger, you may want to install a remote trigger button. This will allow you to perform the testing from a safe distance. When moving the test leads and wire braid, rubber gloves should be worn in order to protect yourself from potential capacitance charge. Before you begin, ensure that the high voltage and low voltage switch or reclosers are open and disconnect the XO bushing. Using wire braid, tie the 3 high voltage bushings together and short to ground. Then connect all 3 low-voltage bushings together with the XO bushing and short to ground. In order to test the high-voltage windings to the grounded low-voltage windings, remove the ground from the high-voltage bushings and attach 1 megger lead. Then connect the other megger lead to ground. Ensure all employees are clear of the transformer and perform the test. Record test results and then ground the high-voltage bushings. Then remove the low-voltage bushing and XO winding from the ground and connect the megger lead. Ensure all employees are clear of the area and perform the low-voltage windings to grounded high-voltage test. Record test results and then ground the low-voltage bushings. Then disconnect the high-voltage and low-voltage windings from ground and short those leads together. Place the megger lead on the windings. Ensure all employees are clear of the area and perform the high-voltage and low-voltage windings to ground test. Record results and ground the high-voltage and low-voltage bushings. Once all tests are complete, remove all wire braid from the low-voltage and high-voltage bushings and reconnect the XO bushing. Record the ambient temperature and compare all results with the previous test results. Because the bushings are not disconnected for this testing, the high-voltage and low-voltage surge arresters are part of the insulation test. If a bad megger result occurs, the bushings should be disconnected and tested again. The surge arresters should then be tested independently. Determine the secondary current of the DS transformer using installed current meters if available or a live line ammeter as shown here. If the station load is 360 amps or expected to exceed 360 amps per phase, then 2 MUS feeder reclosers in parallel must be used to supply the DS low-voltage bus. The MUS recloser trip resistor must be set to 560 amp phase trip with the ground trip blocked. The MUS high-voltage fuses protect the MUS and the DS low-voltage bus up to the DS low-voltage feeder reclosers. No coordination is required between the MUS high-voltage fuse and the MUS low-voltage reclosers. At stations with a primary rating of 27.6 kV, the 400 amp phase trip and 280 amp ground trip resistors are the maximum size that can be used in the MUS feeder reclosers. This will provide the proper coordination with the MUS high-voltage fuses. Prior to laying out the low-voltage cables, ensure that adequate grounding facilities are available in order to conveniently hang and ground all cables. Many crews make up temporary or portable units and ground them to the station ground prior to hanging cables. This is an example of a temporary grounding system used for low-voltage cables. When installed, it should be located in a convenient location to hang the live line end of the feeder cables. Disconnect the cable reel locking pin and place the cable reel control foot switch on the ground. The cable reel electric motor is supplied by the external MUS 120-volt supply. The selector switch has 3 positions: off, and cable on. Each cable and the respective ends are identified using phase marking tape. The neutral cable is identified with green tape. The F1 cables are marked red, white, and blue with a single band of tape, and the F2 cables are marked red, white, and blue with 2 bands of tape. Most mobiles have 3 sets of cables and follow the same phase identification method. Before removing a cable from the reel, establish a clear and convenient pathway, keeping in mind the final connection point. Place the cable reel selector in the cable off position to allow the cables to roll off the wheel. Remove one cable from the reel at a time and drag it across the yard. This requires at least 3 people, 1 person to operate the cable reel control and 2 people to drag the cable. Lay out the low voltage cables in an orderly fashion and avoid overlap where possible. Make sure the phase markings match feeder and phase positions. Do not walk or step on the cables. The cable reel operator must pay close attention to the reel when unrolling the cables in order to avoid snagging or catching. He must also be prepared to stop the reel when the end of the cable appears. Once the cable has been removed from the reel, remove the protective cover on the load end and place the end on a portable ground stirrup or station ground stirrup. Check the high pot test date. This date will either be marked directly on the cable or be included in the annual inspection report. Inspect the cable termination for damage, splits, cracks, or tracking. If necessary, clean the terminator with a clean cloth and isopropanol. Place the termination in a safe, secure location to prevent any damage. Inspect the concentric neutral, ensuring it has a good electrical connection. The complete length of the cable must also be inspected for signs of mechanical damage, splitting, or blistering. If any heat blisters, tracking, or severe tracks are found, contact a cable expert, such as lines or station's cable crew. If significant repairs are done, the repaired cable should be high pot tested. Each MUS low-voltage cable needs to be Megger tested at a minimum level of 1000 volts to prove insulation value and continuity. This requires 2 RMEs, one to operate the Megger and one to short and unshort the concentric neutral to the cable termination. Prior to performing the test, clear communication between the two must be established. Place both ends of the cable being tested on an insulated surface, such as a stepladder. Using rubber gloves, place a jumper lead between the concentric neutral and the cable conductor. Set the Megger test voltage to 1000 volts and connect one test lead to the conductor and the other to the concentric neutral. Test for continuity. Using rubber gloves, remove the jumper. Megger test the cable insulation to the concentric neutral at 1000 volts for 1 minute. Record test results on the MUS record. If any cables are found defective, they must be tagged with a caution tag and removed from the worksite. This will eliminate the hazard of placing a defective cable in service. Once testing is complete, connect the cables to ground to drain the capacitive charge and ensure they are placed in a convenient location. No low-voltage cables are connected until the reclosers have been proven open. If the station does not have pre-made LC-MUS jumpers, a hold-off on the 115 kV circuit will be required while test fitting and fabricating jumpers. These jumpers are required prior to starting the MUS switching. Once they have been fabricated and test fitted, remove the jumpers and store them on site. If a station doesn't have a 115 kV MUS connection structure, the high-voltage leads will need to be installed on the 115 kV tower line conductors. A provincial lines crew should be contacted to install stirrups and assist with high-voltage connections. Several of the 115 kV prepping activities reviewed in the previous module, such as testing cables, will be the same for 44 kV units. However, there are other important prepping requirements that are specific to or more common for 44 kV units. Let's take a look at these now. Most 44 kV units are equipped with 9 fused low-voltage switches. When preparing the mobile, untie the switches and ensure that the fuses are rated properly. For each interrupter, take a resistance measurement in the closed position and measure in the open position. If the load interrupter is seized or the ohmic value is higher than 100 ohms, it should be replaced with a new load interrupter. Test the low-voltage fuses for continuity and open condition using a multimeter. Feeder protection requirements will vary from station to station and may require fuse elements to be changed. Use Appendix C in SP 1609 to select a fuse element with the proper current rating required for feeder protection. Test the fuse element for continuity with a multimeter. Using basic hand tools, disassemble the fuse holder and remove the existing fuse element. Thread the newly selected fuse element onto the spring mechanism and tighten by hand. Holding the fuse barrel vertically, insert the fuse element and spring mechanism into the fuse holder, making sure that the string exits the other end. Thread the fuse spring combination into the fuse barrel and tighten. Turn the fuse over and firmly pull the fuse through the locking ring using the string. This should be done with 2 people. Remove the string if it doesn't break. Tighten the retaining nut. Retest the fuse for continuity with a multimeter and label the fuse with the proper rating. Install the newly prepared fuse. 27.6 kV class fuses are designed differently. Instead of changing the internal fuse element, you will change the complete fuse body. Ensure that the MUS surge arresters are set to the required operating voltage level. For this installation, the shorting jumpers are disconnected for 44 kV. If the MUS was installed at a 27.6 kV station, then the shorting jumpers would have to be connected. Some 44 kV mobiles have high-voltage cables that can be used to connect the MUS high-voltage supply. Only mobiles equipped with a support bracket for these cables can use this method. This support bracket must be installed while prepping the mobile. Remove the hitch pins, raise the bracket to the desired angle, and then reinstall the pins. The high-voltage cables are then prepared, inspected, and tested the same way as the low-voltage cables and connected to the MUS after testing. Using the 2-piece cable stocks, secure each phase over the top of the bracket. Lining up cables, cable stocks, bolts, and bracket will require some finessing. In this case, electrical tape was used to hold half of the cable block in position. The final secured position of the cable should allow for some movement due to thermal expansion. The MUS nameplate will specify whether to use offload taps, links, link boards, or series parallel switches to adjust the low voltage settings. For MUS 29, the voltage was set using offload taps. However, for this unit, MUS 1, the voltage is set by adjusting the links in the main tank. Only 44 kV units have links, and these mobiles will come with a link kit that consists of rope, tape, copper links, and wrenches. There will also be posted instructions on the unit. When adjusting the links, the first step is to pump some of the oil from the main tank into the conservator in order to be able to remove the manhole cover without spilling oil. This can be done several ways. In this case, the RME is installing an air fitting on a valve at the top of the transformer bank and attaching an air compressor to the fitting. He is then pumping air into the top of the tank, forcing oil to go back into the conservator tank. Once the oil gets down past the piping, you will hear air gurgling up the pipe. This is when you should stop pumping air and shut the conservator tank pipe off. You can then remove the main tank manhole cover. The RME at the top of the unit will check the existing link positions and communicate this to the person on the ground. To avoid dropping the wrench in the bottom of the tank, attach it to your wrist using rope.
What I've got is 1, 3, 5 together, 2, 4, 6 together, bridging across 6 and 7. 7, 9, 11 together.
5? Yep.
Yep.
And then you've got 2, 4, 6, 7, 9, 11.
Yep.
The RME on ground will refer to the MUS transformer nameplate to determine what the link positions need to be to match the station voltage. The other RME will then remove the bolted connections using a wrench and turn the links to their required positions. Once the links are in the correct position, put the manhole cover back on and fill the main tank back up with oil. Change the low-voltage link position nameplate located on the side of the transformer to indicate what voltage link position the transformer has been left on. If the mobile you are placing in service does not have high-voltage 44 kV cables, then bare conductor must be used for the high-voltage leads. Depending on the station configuration, these leads will either be connected directly from the MUS to the LC-MUS stirrups, or they will be rotated around a mast and then be connected to the LC-MUS stirrups. In either case, the leads must be fabricated and test-fitted while prepping the MUS in order to ensure that the necessary phase-to-phase and phase-to-ground clearances are available for switching. Let's take a look at the mast procedure. This crew will be installing MUS 8 at Tory Hill DS. MUS 8 is a 44 kV unit equipped with a mast. Tory Hill DS is a U70 style station. Before beginning any work, hold a tailboard with all crew members to review the steps required to establish a self-administered work permit.
You're going to have your full body harness on. There'll be a guy up on the top of the MUS. We're also going to have full body harness on and proper footwear. It might be a little icy out today.
This includes checking the LC-MUS open and hanging work protection tags. Once all 3 tags are hung, the permit holder must complete the proper paperwork and call the OGCC to log the permit and get a hold-off on the 44 kV circuit. Check the bottom stirrups using an LIV to confirm they are dead. Then test the LIV to the live stirrup to make sure it's working properly. Once the bottom 3 stirrups are confirmed dead, install grounds on each stirrup. Install a ground mat and open and lock the MUS8 T1-L switch so that it's open while you connect the conductors.
Okay guys, you're going to be opening the MUS8 T1-L. T1-L coming open.
Now it's time to install the mast. This will require 3 people, 1 in a man lift and 2 on ground. First, remove the mast from its shipping position and stand it up on the ground. Be aware of adjacent live electrical equipment and maintain required clearances. Extend the top and bottom brackets out about a foot. Raise the mast, set it into the bottom bracket, and pin it. Then clamp it to the upper support bracket. An alternative method of raising the mast is to use the provided manual crank handle winch. Install the 3 mast insulators, starting with the blue phase, then white, and finally red. This can be a trial and error process because once all 3 leads are installed, you might not have the proper phase-to-phase clearance. Depending on the placement of the mobile, you might have to use more than 3 insulators to bring the leads around the mast. Select flexible primary conductors of sufficient amperage capacity to supply the station load. The minimum is number 2 copper. Attach live line clamps to one end of each conductor. Take the blue phase conductor first and connect it to the LC-MUS stirrup using the live line clamp. Pull the other end of the same conductor back to the mast insulator tightly and clamp it to the insulator. Then connect the conductor to the T1-L connection point, ensuring correct phasing is maintained. The leads should be fairly tight to allow for the required clearances. Repeat the same steps with the white and red conductors. When connecting the conductor to the LC-MUS stirrup, use a 6-foot grip awl. The shorter stick can't reach the live 44 kV circuit, which is an additional barrier for the live hazards. Once all 3 conductors are connected, visually verify the phasing arrangement to make sure no phases have been crossed. As you can see, clearances are pretty tight on the mast. Using a measuring stick, check the required phase-to-ground and phase-to-phase clearances as outlined in SP 1609. Reconfigure the mast if the clearances are not correct. In this case, they don't have the required 22-inch phase-to-phase clearance. They will need to move the white phase support insulator up by 1 hole. This requires one person to support the conductor and one person to move the insulator. Reclamp the conductor to the insulator and connect it to the switch connection point. Then check the clearances again. After you have confirmed that the phasing arrangement and clearances are correct, cut off the conductor tails at the switch end. Alternative methods for obtaining the proper electrical clearances may include lengthening devices to get the conductor further out. Drop the leads down one at a time. As each one comes down, mark them with phase marking tape so that they don't get mixed up when you put them back up. Secure the loose ends to the MUS, someplace where the wind can't blow them into the live conductor. Once all three leads are down and secured, remove the three portable grounds and surrender the work permit on the primary side of the DS. Create a switching order to remove the three tags hanging on the LC-MUS. This will be the only item on the OTO. Call the OGCC to surrender the permit and hold off. Dropping the leads is considered a best practice. However, you may choose to keep them connected to the MUS structure. If you do keep them connected, do not surrender the work permit. It is up to the crew on site to decide what will work best for them. Some station configurations allow for direct connection of the high-voltage leads. The direct connect method is much easier because you don't have to rotate the leads around a mast. Instead, you would establish a work permit on the LC-MUS, install three temporary grounds to the LC-MUS stirrups, and then connect each conductor, first to the LC-MUS stirrup and then to the MUS high-voltage connection point. Once the leads are cut to the correct size, you can also drop the leads and surrender the work permit or keep them up and maintain the permit. Once the MUS is prepared for switching, it is best practice to perform a final walk-around to confirm that every necessary task has been completed properly. Check that the MUS grounds are still connected securely to the station ground. The high-voltage and low-voltage portable ground mats are in position and connected to ground. The MUS ULTC voltage sensing relay settings are matched to the station sensing relay settings. Clearances are maintained. Tools and equipment are clear. The wire braid is removed from the transformer and bus work. The XO bushing has been reconnected. The high voltage and low voltage switches are open and locked. The surge arresters are set for the proper operating voltage. All targets and drag hands are reset. Oil levels are correct. the external supply is disconnected, and the internal-external switch is set to internal, and the gates and barriers are secured in the proper position. After a thorough walk-around has been completed, you are ready to install the mobile. Let's go back to the MUS-29 example and review the procedure for installing this 115 kV MUS at Battersea DS, a U70 station. Prepare a PC-17B work permit to isolate the MUS. This will provide a safe work area to fabricate and install the high-voltage leads. Check all 3 LC-MUS jumpers are removed, and then install 3 tags to confirm them removed. Check all 3 phases on the MUS T-L high-voltage switch are open and leaning back. Lock and tag the operating handle. Check all 3 phases on the MUS T-B low-voltage switch are open. Lock and tag the operating handle. The permit is accepted once all 3 steps on the PC-17B have been completed. Use number 2 bare copper conductor for your high-voltage leads. Measure the required length and cut the conductor to size. A common practice for determining conductor length is to use 3/8" rope and 2 switch sticks to measure the distance between the connection points. When cutting the conductor to size, allow a little extra length for final adjustments. They should be long enough to prevent strain on the insulators, but short enough to maintain electrical clearances. Install live line connectors on the structure end of the leads. Take some time to align the live line connector to the stirrup it's going on. This will prevent torque on the conductor, making it easier to install and remove. Insert each conductor into the high-voltage pads on the switch jaw. Verify the orientation of the clamp before tightening the connector pads. The ends of the leads need to be controlled at all times to ensure they don't swing into live conductors or become a falling hazard to anyone. Connect the high-voltage leads to the MUS structure stirrups one at a time. One hazard to be aware of is potentially having the underslung insulator fail and fall to the ground. Make sure you have your escape routes planned at all times. Once all high-voltage leads are installed, visually verify the phasing arrangement and ensure proper phase-to-phase and phase-to-ground clearances are maintained. Then surrender the self-administered work permit. Once the high-voltage connections are made, you must energize the MUS to verify that the reclosers are open. Prepare and check an OTO for removing the work protection tags energizing the MUS, and verifying that the reclosers are open with the springs discharged. Check that the external supply is disconnected. Close the fused disconnect isolating switch located in the mech box of the MUS. Check that the internal-external switch is set to internal. Obtain a hold-off on the high-voltage 115 kV circuit. This hold-off will remain in effect until all switching is completed. Check that all high-voltage fuses are closed. Place the MUS T1 ULTC control switch into the manual position. Remove the LC-MUS work protection tags. Then install the LC-MUS jumpers on all 3 phases. This will energize the jaw of the MUS T-L. Check that the MUS primary disconnect switch is open and remove the work protection tag. Wearing rubber gloves and standing on the grounding mat, close the high voltage switch. Check that all 3 phases are closed and turned in, and lock the handle in the closed position. The MUS is now on potential. Check the MUS phasing switch for proper rotation using the phase rotation meter located inside the transformer operating mech box. If the phasing is incorrect, you must take the MUS off potential and adjust as required. Check for 120 volts on all 4 positions of the MUS voltage selector switch. Test the MUS cooling system components. On MUS 29, there are 2 cooling pumps and 2 cooling fans. Place the controls in the on position and verify that the green lights are on. Check both oil flow indicators to ensure pumps are functioning. The indicators are located on the curb side of the unit directly on the cooling pipes. Check both cooler fans for correct rotation. Reset the MUS 86 lockout relay. Place the MUS F1 and F2 OCR local remote lockout switches in the remote lockout position. Check that the MUS low voltage disconnect switch is open and remove the work protection tag. Close and lock the low voltage disconnect switch. This energizes the low voltage bus and source bushings on both reclosers. Check that the F21 and F22 OCR AC supply fuses are removed. Perform the close trip operation on the F1 recloser. Set the close trip selector switch to the close position and then to the trip position. Verify that the F1 recloser tripped and the closing springs did not recharge. This confirms that there is no chance of the recloser accidentally closing during cable installation. Verify zero potential on the F1 load terminals with an approved LIV tester. Set the LIV to the correct operating voltage and test it on a live circuit first to ensure it functions correctly. Repeat the same close trip operation again on the F2 recloser to verify the recloser is open and the springs are discharged. Then check F2 for zero potential using an LIV. After the reclosers have been verified, it's time to connect the low-voltage cables. Establish a self-administered work permit that allows you to safely connect the low-voltage cables. Open the MUS T-B low-voltage switch. Check Open, Locked, and Tagged. Check that the F1 OCR is open with the springs discharged. Check that the F21 and F22 fuses have been removed from the fuse holders and place work protection tags at the insertion points. Place the station's reclosers in the non-reclose position. Use an LIV to prove isolation of the MUS low-voltage bus. And then apply temporary working grounds. Secure the grounds with a half-inch piece of rope and tag them with a de-energizing tag. Open and secure the MUS recloser gates. Remove the cable support blocks. Connect the neutral cable to the MUS neutral connection bar. Connect the MUS low-voltage cables to the corresponding MUS F1 recloser connection pad, making sure the phasing and feeder numbers match. Once all cable connections have been checked secure, connect each cable concentric neutral to the MUS ground bar, located near the top of the reclosers. Reinstall the cable support blocks, allowing for some movement due to thermal expansion. Ensure that electrical clearances are maintained and the cables are not pinched, squeezed, or damaged by the wooden blocks. Close and secure the MUS recloser gates with the upper barrier secured in the outermost position. This is required to maintain electrical clearances when the load recloser bushings become energized. Remove the de-energizing tags and the temporary working grounds from the MUS low-voltage bus. A common practice at a U70 or U90 station where the neutral connection is made low to the ground is to apply a caution tag to indicate that the neutral is in service and cannot be removed. Before connecting the cables to the DS feeders, inspect the bus and insulator for damage or missing components, and ensure workers have a clear path to exit the area in case of an event, such as a broken insulator, a stirrup malfunction, or cable failure. Connect the MUS neutral to the DS neutral, and then connect the low voltage cables to the appropriate DS feeder positions. 2 workers are required for this job step. One worker will help raise and control the cable into position, wearing rubber gloves. The other worker will raise and position the connector onto the live low-voltage bus stirrup using a switch stick. Initially, the switch stick hook is attached to support rings on the cable termination. Once the connector has been attached to the live station bus, the worker supporting the low-voltage cable will supply a slight downward pressure to help keep the live line clamp seated on the stirrup. The other worker will then release the switch stick hook from the cable connector and attach it to the live line clamp. The clamp is then tightened and checked to ensure it is properly seated and secure. When raising the cable using a switch stick, it's important to use the provided rings and not the live line connector. This is because the weight of the cable could distort the threaded shaft of the connector. If the station has 2 feeders, use the same procedure to install the second set of low-voltage cables. Only 1 neutral cable is used, and only 1 set of cables can be used per MUS recloser. The low-voltage station bus MUS connection stirrups are designed to accommodate 2 cables per phase if required. Each cable is phase marked with colored tape and should correspond with the phase markers on the DS structure. Once all low-voltage cables have been installed, surrender the established work permit. After the low-voltage cables are connected, the MUS is ready to be switched into service. Prepare and check an OTO for removing existing work protection tags and switching the MUS into service and the DS out of service. Remove the work protection tag on the low-voltage disconnect switch. Unlock and close the switch and then lock the operating handle in the closed position. Verify the phasing across the opened MUS recloser. Phase checks must be performed between all 3 phases. It is easier and safer to perform these checks from the end of the MUS low-voltage bus to the recloser low-voltage cable side. These RMEs are using a tag 5000 to phase check. When using this test equipment, verify that the annual inspection and calibration date of the transmitter and receiver are within the year. Both the transmitter and the receiver require a verification test to ensure the units are functioning properly. They should also be tested on a known source. After the unit is confirmed functional, you can perform the required phase checks. Place the transmitter on each conductor to verify the presence of voltage. The transmitter will begin beeping with flashing lights when voltage is detected. After testing one conductor, remove the transmitter from the line and wait for all LED lights to extinguish before placing the unit on the next conductor to be tested. After all lines are confirmed as being energized, place the transmitter on the first conductor to be phase checked and wait for the beeping tone and flashing lights to stop. One light will remain on, indicating the unit is transmitting. Then place the receiver on the opposite side of the open point. When placed on an energized conductor, the unit will beep once when voltage is detected, and one LED light of the receiver will turn on to signal the unit is operating in the receive mode. If the conductors are in phase, the other 3 receiver lights will turn on, and the unit will emit a steady tone. If the conductors are out of phase, the receiver will supply a brief burst of all lights and a single short beep, but will not emit a steady tone. The TAG 5000 is not capable of indicating large in-phase voltage differences. Approved chance phasing sticks are the recommended testing equipment. Check that the MUS F1 non-reclosing normal reclosing switch is in the non-reclosing position. Remove the work protection tags from the insertion points of the recloser AC supply fuses and install the F21 and F22 fuses. This will charge the recloser springs. Turn the desensitizing relay on to ensure it is functional. Then push the desensitizing relay cancel button and reset the TX relay. Place the station ULTC control switch in the manual position. This switch is located in the station's transformer mech box. Check that the MUS ULTC is in the manual position. Measure the secondary voltage of the station. If required, adjust the MUS secondary voltage using the ULTC to maintain proper parallel voltage between DS and MUS. The MUS should be approximately 3 to 5% higher than the DS. Metering units and bus PTs may have a non-standard ratio. This will require calculation. Close the MUS F1 recloser. If the single-phase load to be switched in is greater than the MUS feeder ground trip resistor amperage, then block the MUS feeder ground trip feature until after the single-phase switching has been completed. Check current on all cables using the amp stick sensor link horseshoe CT. The MUS and DS are now in parallel. At U70 stations, the station reclosers remain in service. The only equipment isolated is the station transformer. Open the DS low voltage switch. The MUS is now carrying the station load. Then open the DS high voltage switch. The station transformer is now off potential. Place the MUS F1 non-reclosing normal reclosing switch in the normal reclosing position. Place the MUS ULTC controls in the auto position to regulate station load. The tap changer should not raise or lower more than 2 taps. Check that the MUS F1 ground trip blocking switch is in the normal position. Place the station reclosers into the reclose position to restore normal operation. Surrender the hold-off on the high-voltage 115 kV circuit. Contact the controlling authority to inform them of the DS and MUS status. If the controlling authority is Provincial Lines, the DOMC must also be informed. Establish a self-administered work permit on the DS equipment if required. Install additional barriers to prevent vehicle or pedestrian traffic from approaching the MUS installation or crossing the low-voltage cables on the ground. A DGA sample must be taken from the main tank and ULTC compartment after the MUS has been placed into service, ideally between 24 and 48 hours, but due to resources and scheduling, between 4 and 72 hours is acceptable. We will now look at the steps for removing MUS-29 from service. Ensure that tools and equipment are clear, all connections have been made, and switchgear is in the proper position. If a capital project has taken place, ensure that all commissioning has been completed and perform phase checks. Call the controlling authority to inform them that the work permit has been surrendered on the DS and that it will now be switched into service. Remove barriers to allow easy access to the low-voltage cables and the MUS control cabinet. Prepare and check an OTO for switching the DS into service and the MUS out of service. Obtain a hold-off on the high-voltage 115 kV circuit. This hold-off must remain in effect until the MUS conductors and cables have been disconnected from the DS. Check open the DS high-voltage disconnect switch. Place the DS reclosers in the non-reclosing position. Place the DS and the MUS tap changers in manual. Check that the MUS reclosers are closed and place them in the non-reclosing position. Close the DS high-voltage disconnect switch. Check and adjust the DS voltage to match the MUS. The DS voltage should be approximately 3 to 5% higher than the MUS voltage. Close the DS low voltage switch. The MUS and DS are now in parallel. On the same OTO, open the MUS reclosers and check for zero current. Place the DS tap changer in the auto position. Open and lock the MUS low voltage switch. Open and lock the MUS high voltage switch. Remove the LC-MUS loops. 3 people are required for this operation, 1 on each live line clamp, and 1 to remove the loop once it's lowered to the ground. The MUS is now out of service, and the DS is carrying all station load. Establish a self-administered work permit to guard against any possible backfeed while disconnecting the MUS high-voltage conductors and low-voltage cables from the DS. Check all 3 LC-MUS jumpers are removed, and then install 3 tags to confirm them removed. Check all 3 phases on the MUS T-L high voltage switch are open and leaning back. Lock and tag the operating handle. Check all 3 phases on the MUS T-B low voltage switch are open. Lock and tag the operating handle. Remove the MUS F21 and F22 fuses. Check that the DS reclosers are still in the non-reclosing position. Check that the LC-MUS loops are removed. Prepare and check an OTO to remove the conductors and cables. Remove the MUS low-voltage cables from the DS feeder stirrups. When removing the cables, loosen the live line clamp and hook the grip awl onto the hardware ring fastened to the top of the cable. Don't take the weight of the cable using the live line clamp, because you could bend the clamp. Take the weight with the provided ring and control the descent of the cable to ground. Discharge the cables to the station ground or de-energizing stirrups. Do not use the fence to ground the cables. Remove the high voltage leads from the MUS switch jaw. Control the lead completely to the ground and park it on the MUS. The neutral cable is removed last. Place the DS reclosers in the reclose position. Discharge the MUS reclosers by performing the close and trip operation. Verify the F1 and F2 reclosers tripped and closing springs did not recharge. Surrender the work permit. Call the controlling authority to surrender the hold-off and inform them of DS and MUS status. Now let's take a look at the procedure for installing a 44 kV MUS. This crew will be installing MUS-1 at Elginburg DS, a Jones-style station. They will be using the 44 kV cable method. The MUS end of the primary and secondary cables have previously been connected while preparing the mobile. You must now establish a self-administered work permit to connect the primary and secondary cables to the DS. This will require the LC-MUS loops opened and tagged, the low-voltage MUS feeder switches opened and tagged, and the high-voltage switch opened and tagged. Some crews also choose to control the position of the feeder gates with work protection tags. Obtain a hold-off on the 44 kV circuit. This hold-off must remain in effect until all switching is completed. Place the station reclosers in the non-reclose position. Prepare and check an OTO for connecting the high voltage and low voltage cables to the DS. Connect the neutral cable to the corresponding DS neutral position and then connect the MUS low voltage cables to the energized DS low voltage feeder stirrups. Because the DS feeders exit overhead at this station, a bucket truck is required to hang the MUS feeder cables. Connect the high-voltage cables to the LC-MUS stirrups. Be aware that the 44 kV cables are significantly heavier than the low-voltage cables. Once the high-voltage cables are connected, secure the cables to the wood pole to help relieve tension on the connectors. Surrender the work permit. Prepare and check an OTO for switching the MUS into service and the DS out of service. Check that the external supply is disconnected and the internal-external switch is set to internal. Check that the high-voltage disconnect switch is open and locked. Check that the low-voltage feeder disconnect switches are open and locked. Remove work protection tags on the LC-MUS loops and then close the loops. This will energize the primary cables to the MUS switch jaw. Be aware of your physical proximity to the cables when performing this task. Close the MUS high voltage disconnect switch. Verify that the switch blades are in the correct position and lock the switch handle. The mobile is now on potential. Using the auto hand controller located in the transformer mech box, turn the fans to hand and ensure they are functioning properly. Then place the fans back to auto. Using a multimeter, test the secondary voltage of the MUS and the DS to ensure that they are as close as possible. Ideally, the MUS should be higher than the DS by less than 5%. Mobiles that are not equipped with a ULTC, like this particular unit, must be taken off potential in order to readjust the voltage if necessary. This is why it is important to perform all necessary calculations and ratio testing when selecting your tap positions prior to switching. Perform feeder phase checks on all 3 phases. If the phasing is incorrect, it will have to be adjusted with the MUS off potential. Remove work protection tags on the MUS low voltage switches and close the switches. This will put the MUS and DS in parallel. Using an amp stick meter, verify current flow on the feeder cables to ensure they are carrying load. remove the work protection tags on the feeder gates, and close and lock the gates. Open the station reclosers to break parallel between the MUS and the DS. While doing this, another RME is measuring the feeder current with an amp stick ammeter to ensure that the reading goes to 0 when the recloser is opened. Open and lock the station high voltage disconnect switch to take the station off potential. Surrender the hold-off on the high-voltage circuit. Different station configurations will require the opening of live line loops, switches, or mid-span openers to completely isolate the DS. This station has MSOs on the low-voltage feeders that need to be opened. Establish a work permit on the DS if required and hang work protection tags. We will now look at the steps for removing MUS1 from service. Prepare an OTO for switching the DS into service and switching the MUS out of service. Obtain a hold-off on the 44 kV circuit. Check that the DS reclosers are open and in the non-reclosing position. Close the station high voltage switch. This will put the station back on potential. If required, adjust the secondary voltage on the DS to maintain proper parallel voltage between the MUS and the DS. Close the DS feeder reclosers and check for current. The MUS and DS are now in parallel. Open the feeder gates and check the feeder cables for current flow using an amp stick meter. Open the low voltage disconnect switches to break parallel. Then test the cables again to ensure that there is now zero current. Open and lock the MUS high voltage disconnect switch to take the MUS off potential. Open the LC-MUS loops to isolate the MUS from the 44 kV circuit. Remove all high voltage and low voltage cables and de-energize them using temporary portable grounds. Cold load pickup issues occur when the load being picked up exceeds the MUS fuse protection. When power is restored after an unexpected outage, the load is higher than normal because all appliances, heating and cooling devices will immediately try to operate. The longer the power is out, the higher the load current will be when the supply is restored. If you try to pick up too much load at one time, the fuses or reclosers may operate. In this case, you will have to pick up the load in smaller sections. This will require coordination with lines to sectionalize the station load. Single-phase switching of station feeder reclosers may be required to allow feeder loads to individually dissipate. When performing single-phase switching with one 3-phase MUS recloser supplying 2 DS feeders, it may be necessary to temporarily block the ground trip feature on the 3-phase recloser until the single-phase switching is completed. As a rule of thumb, if the single-phase load to be switched in is greater than the MUS feeder ground trip resistor amperage, block the MUS feeder ground trip feature until after the single-phase switching has been completed. Viper reclosers are pre-programmed with provisions for cold load pickup, so they do not require manual changes to be completed. In emergency situations, you will not be able to perform phase checks at the station. Once the MUS is on potential, provincial lines will have to phase check outside the station on adjacent live circuits or sources at the nearest tie switch. If phasing is incorrect, you will have to take the MUS off potential and correct the connections. Lines will then perform another phase check. After the MUS is removed from service, the unit needs to be packed up and prepared for transport. Use the unit-specific shipping checklists to make sure all required action items are completed properly. Place and secure the shipping covers onto the cables. Position the appropriate cable on the cable reel slot and fasten the tether lead onto the reel. Ensure the cable reel is rotating in the proper direction. Then gently lay the cable on the cable reel layer by layer. Once the bus end of the low-voltage cable reaches the reel, secure the free end of the cable to the reel using a ratchet strap or a piece of rope. When installing the shipping braces, you will be handing them up from the ground. Be careful not to damage any insulators or surge arresters as you pass them up. Match the markings on the stacks to the brace. The two red-handled valves that supply oil for the cooling should remain open until the tractor is ready to remove the mobile from the DS. These valves are only to be closed during transportation to prevent oil leaks from developing due to oil expansion caused by rising temperatures. Units equipped with Unifin coolers have oil valves between the aftercoolers and the main bank that need to be closed as well. If the unit is equipped with a bypass valve, it must be closed during operation and opened during transport. The most critical step in preparing the MUS for transport is closing the breather. If the unit is going to be stored overnight during transit, arrangements must be made by the shipper to relieve any pressure buildup on the unit at its storage site. Just like receiving the MUS, when shipping it from the DS, arrangements must be coordinated with the driver, a traffic control plan prepared, and sufficient workers should be on site for traffic control. The driver will position the tractor adjacent to the MUS kingpin, make the air and electrical connections to the MUS trailer, and apply the trailer brake. He will then back the tractor onto the kingpin. The driver must visually check that the fifth wheel connection has been locked and secured.
Normally, most truck drivers, operators, when they hook up to a trailer, when they pin their fifth wheel to the truck, normally they put it in first gear and pull forward on the truck to make sure that the fifth wheel is locked. With the MUSs, we encourage the drivers not to do that, but get out and check them with their hand. that they're locked, because what happens is the weight of that MUS on those two little outrigger legs, when you pull forward, you're bending the outrigger legs and it causes them to break off right then and there, or down the road. It could, the next time when you go to drop them, they could break off. After the operator ensures that the parking brake is on the truck, he supplies the air to the trailer and comes back here to the manual air override switch. And with this here, we switch this to manual, which is on, or from automatic to manual, which shows you which way right here. And then we turn this valve all the ways in until it won't turn any farther. And what that does is supplies air to the airbags to fully extend them to raise the trailer high enough in the air that you can crank the landing gear up with no tension on them whatsoever.
The operating handles are stowed, and the landing pads are removed and stored. The driver then places the air ride control switch into the automatic position for transport. A final inspection should be performed before the MUS leaves site.
All right, we just received MUS 21 at CMS here, and we're going to show you how to do the annual maintenance on it. First thing you like to do is to make sure all the logbooks and everything is in order, and what has gone on over the year to make sure everything's good. You want to make sure first off you have the shipping and service binder, the instruction manual for the MUS that you're working on, and your logbook for the TWE and all that stuff. Now you'd like to go through them just to make sure what happened over the year and what has gone on, any defects is noted in there, all that other stuff. And then after that's done, nothing major, we're gonna go ahead and test. And we do the 4 major tests. We do a Megger, a full ratio, cap DF, and ohm meter. And you're gonna wanna do that right away just to see how the MUS is holding up. Next, we're going to look at the mech box. We're just going to make sure that first off, the door gaskets, everything's fine, all hinges are greased, lube, that's what you're going to want to do. You're going to look inside, make sure all breakers, light bulbs, heaters, everything's working, just in routine maintenance we always do. Every year too, we have to do an SI on the ULTC if there's one. We just got to make sure that the nameplate's legible, everything's good and accurate. Make sure there's no leaks or a new gasket once you do the SI, and your drain valves, you want to go ahead and make sure that nothing's leaking on them, repair them if they are, and just once over on everything. Next, we're going to look at the ULTC if they have one. First thing you want to check to make sure is if your nameplate data is all lining up with the unit you have on the MUS. You want to inspect the limits electrically, just operate it. Make sure that you're going to pull this open and do an SI on the tap changer. Just do a quick inspection, some measurements. There's all documents for which one you're working on. You're going to inspect also the drain valves, make sure nothing's leaking, repair them if they are. And check to make sure your oil level is good at the end. And inspect everything for damage or wear and repair. Next, we're going to move on to the cable reel, and what you want to do here is remove this cover. It's good to inspect the chain and the transfer case on the electric motor. Just make sure everything's greased, everything's topped up, and just inspected. The other thing too is that you got grease fittings on both bearings on your cable reel. You want to grease those for sure. Moving on, we're going to look at the cables here. We're going to high pot them every year, clean them up, and first you want to inspect the covers, make sure they're not that moldy, ripped. If they are, replace them. And moving to your cable, you want to just make sure the stress cone's all good, all your sap tape, everything is intact, not ripped, torn. Just check the connections, torque them, and your live line clamp, just make sure that you can move it and clean it up, grease it, and you're good. Another note with the cable reel is just to inspect the bungees, make sure that they're not weathered and cracked, replace them as necessary, and make sure to stock some extras on there because throughout the year they snap on you, so it's good to carry lots. Up next, we got the high voltage fuses compartment. You want to open that up and just you want to inspect the fuses that are dressed. You want to just make sure they're cleaned, everything operates and is oiled. You want to also make sure that every fuse that is carried on the MUS is blow tested or airflow tested, and you want to put a new inspection date sticker on them. And just you also have to make sure that for every amperage you're carrying, at least carry 4 altogether. You have 3 and then an extra spare so you can dress any 3 fuses. And you usually like to keep between 100 to 200 amp high side fuses on it, depending on the MUS you have, I guess. And just to go through the compartment, just bag the spares every year, and then they get open over time. Clean out anything that's left over. You get a lot of spares, weird sizes. You got some 34.5s, 44 kV. Just clean them all out and put on what's needed. Next is you want to inspect the landing pads. Over time, they get pretty beat up. Half the time, they're not even on the unit since it's winter time. But we have one right here that's pretty beat up. Could be replaced or just fix the rope. And just order new ones, like so. Next, we're going to look at the outriggers. You want to go ahead and just, the only thing to really look at is the pin. Make sure it's not bent. If it is, replace. You can find them anywhere. And as for greasing, when it goes in for its MTO inspection, they usually take care of that, so there's no need to worry about these grease fittings. Next, we're going to look at the grounding on the MUS. We're in the area right now. You want to go ahead and inspect all the connections and the tightness of the bolts. Over time, these things get stolen in the field, go missing, and you got to repair them real quick. So this is a good time to sit down and inspect all the repairs that were made and the quality of them. Next, we're going to do we have to do an annual GOT, and on the tap changer, you want to do an annual UTOA, and that's done every year. And you also want to look at the nameplate, make sure it's legible. If it isn't, you have to go ahead and order a new one. And up here we have our OCTC parallel and series switches. You want to go ahead and operate those. We've been having a lot of problem in the field with these seizing up after not being used for a while. You get salt and water and sand all in there. They're very difficult. That's the whole reason why this one is in CMS, because we had a broken shaft. So we're going to start operating them in the field a little bit more, get some play in them, because every time we bring them in and we're able to move them, we end up cleaning them up, greasing them, and within a couple months they're all seized up again. So it's good that every time you're throwing one of these MUSs in to inspect the handles and make sure the shafts are moving freely. Next, we're going to be looking at the conservator. We want to go ahead and just inspect make sure all the bolts are tight. You want to look at the mounting bolts holding the conservator to the tank. We want to go and look at the sight gauge, make sure there's no leaks, make sure everything's tight. You want to inspect the piping, make sure everything's tight, no leaks, no damage. Next, we're going to move on to the rads. Good thing to look for is cracks, leaks, any damage, dings that they pick up going down the road. If your rads do have valves, this one doesn't, it's a good thing to inspect them, all your flanges, everything, just torque them, and make sure the valves operate smoothly. Next, we're going to look at the neutral. We're going to inspect the neutral bushing clamp. A lot of times that will get overstretched from over-tightening from being removed and reconnected so many times. And just to inspect the neutral as it comes down the transformer. And once it gets to the bottom, it's a good thing to inspect the connection made to the ground bus, because like we talked about earlier, theft and other things down in the field that you might not pick up and notice. Next, we're going to move on to the low voltage side of the MUS, and first thing you want to do is go ahead and inspect your gate, and just to make sure that everything's operating all right, you want to grease all the hinges. You want to inspect the welds on where the lock's going to hold the gate open for yourself when you lock it. Make sure they're good. Just grease anything that's movable, because again, salt and dirt gets in there, and you want to inspect and make sure you have all your fuse amperage signs. Next, we're going to look at our low voltage fuses and switches. First thing you want to do is just do your typical overhaul on your switches. You want to inspect just the linkages, grease, oil, and clean like you always do. Your load breaks here are supposed to be changed every 3 years. The date's written on the side of them when they are replaced. And for your SMU5 fuses, you want to just inspect the contacts, clean them up, usually wring them out. I like to also pull them apart and just inspect what fuses are actually in there, because you don't know what you're dealing with when they come in logbook wise. And just to clean the contacts too where the the cables come up and connect. You can also look at your insulators back here. These ones are poly, but if they're porcelain, inspect them for cracks or signs of wear. Next, you also want to inspect the phase markers on the low voltage side just to make sure they're correct or they haven't been worn off. Same with the nomenclature. Sometimes duct tape's put on them, covering some numbers and letters up. You want to go ahead and inspect that. And also, just from going down the road, it seems like every year we have to realign the fuses and the switches a little bit, loosen them off and re-straighten them because they seem to all be crooked and not lining up the best with when you're trying to handle them with a P2 stick. So next we're going to inspect the high voltage mast. What you want to do is just ensure that the pin's still there. Sometimes they go missing. You also want to inspect the bracket holding the mast up. You want to lube and grease it so it's easy to operate. Back here, if you can see it, is the winch, and you want to go ahead and just ensure that everything's tight. You want to lube and grease the wheel itself, and just make sure it operates smoothly. And just at the very bottom here, you want to use inspect your mast pin, like just the pivoting. Just to go ahead and grease that and make sure that it's all bolted up and tight. Next, we're going to talk about the MOT sticker, which is right here. Every year for an annual, it goes in and get inspected by a certified mechanic, which involves them inspecting the air receiver, brakes, anything trailer related that we don't deal with. After the MUS is sent away and is inspected by the MOT and you get a sticker on it, you want to go ahead and open up a housing, usually located right beside it, and just look for the paperwork that they'll provide, and that's the MOT annual inspection certificate, and you'll have the mechanic that inspected it signed and dated. You also want to look in there and you should find the vehicle plate permit. They both go in there, and you just want to verify they're there. Now we have the MUS spill kit. Most they're located on every MUS. You just want to go ahead, open that, and just inspect the seals around. Make sure there's no moisture or water sitting on the bottom of the bin. There is a check sheet that we pull out and just verify all the items that are in the spill kit. So there's initial, and just go through and itemize everything, and to verify everything's in there. Next, we're in front of the high voltage mast bin. There's also a fire extinguisher in here, so it's good to have, make sure there's labels on the doors so you can easily access the fire extinguisher when needed. Another good idea too is to label the bins. This one doesn't have any on it, but to say high voltage mast so someone can easily know what's in there without having to open up every bin. Once inside, again, just make sure all the gaskets, everything's good, all your hinges greased, everything's operating fine. And this is more miscellaneous too. You have, just make sure to over the year things get pretty messy. Just to clean everything up, label the bins. Make sure you have enough insulators for the mast, parts. It's good to carry idea to carry a couple spare low voltage fuse parts, some live line clamps, and your bolts for your high voltage mast to bolt the insulators on. Another note is to actually get the fire extinguisher inspected every year. After going on the road for a year, you don't know what happened to it or what's going on, so it's good to send it away and have someone look at it. All right, up next we have the lightning arrestor bin. Same thing as all the other bins we've been looking at, is just make sure that they got good seals and grease. Obviously that one's a little squeaky. What you want to do is just make sure that this thing is carrying the right LAs for the voltages that are on the MUS. So multiple voltages, you're going to have multiple LAs. And what you're going to be looking at is the MCOV rating, which you can find in your what LAs you need in your manufacturer manual, or if not, you can contact MTS and they'll guide you to the right LA you need. All right, next we have the MUS ground mat. Every MUS should be stocked and supplied with one of these. On the annual, you want to go ahead and open it up, lay out the mat, inspect the connections, all your leads, everything is good, and you got good continuity on your mat. And once that's done, we can move on to the switch here. First things first, you got to make sure that the switch is grounded. There's a good connection, because again, with theft, it could go missing. Any grease nipples or anything like that, you want to go ahead and grease it. Operate the switch first, make sure how it's running or operating smoothly or how rough it is. Make sure there's nomenclature on the switch. As you can see, this one's just Dynatape, so it needs to be improved with some decent nomenclature. And just as you go up the switch, just make sure that your typical overhaul, your insulators are good, no cracks. These ones are poly. Make sure every pivoting point, everything's greased, and you do a good overhaul on the switches. Next, we're looking at the high voltage fuses. A good thing to do is obviously overhaul them, clean them up, grease them, but is also to do a dry run with the an actual fuse just to make sure it pops up and out and not staying in there and everything's mating correctly. And as you're going along too is just to make sure that all bus and everything's tight and is torqued and connected, because these things rattling down the road, everything seems to loosen off quite a bit. Now we have the hydraulic power pack found on some MUSs with hydraulic outriggers. So what you want to do for the inspection on this is inspect the gas, make sure there's gas in it, or if the gas is old, drain it. We like to be putting new gas in it with stabilizer every year. Change the oil on the motor too, that's a biggie. A lot of times we get fuel in it because people aren't shutting off the fuel shutoff valve, and that gets pretty full. You want to go ahead and replace the hydraulic filter, and the battery, go ahead and charge that, but if it's bad, replace it. And also you want to go ahead and top up the hydraulic fluid, or check the level anyway, and just do a general overview of if there's any leaks or pools of oil underneath the engine or the hoses. All right, we have the ULTC control mech cabinet. What do you want to do? We talked about a little bit earlier is operating electronically to its limits, even manually to make sure it's not binding or anything like that. Make sure the counter's working. The heater also in that control mech is something to check for. And just to make sure the position gauge is moving and your limits are indicated at max and minimum. And that duct tape there you see too, it's always good practice to throw some gasket material over the glass so it doesn't break from rocks down the road. Now we're looking at the qualitrol. What you want to do too is just inspect the qualitrol, make sure it's the flags aren't up or anything like that, that there's seated and oil leaking out. A lot of people have a habit of leaving the valves closed, and qualitrols do tend to go on these things sometimes. This one is a newer mod they put on them. It's they put an expansion chamber on it with an indicator, so you don't have to see the flag like from a ladder up top. You can see it from the side here. And they equip it with a downpipe now, so it kind of isolates your spill to one spot and not all over the whole area. Another thing annual maintenance will ask you about is the UCL plate. They are installing them on new units or ones that are being refurbed if there is room, so it all depends if you have one or not, if they're going to put it on. All right, now we're at the low voltage fuse cabinet. Again, just make sure that the cabinet's operating fine. Grease it, make sure the gaskets are fine, no moisture or water in the bottom. What you want to do too is just go through the stock. You start picking up extra fuses and bad ones along the way, and you want to wring them all out just to verify that they're good, and you can put them back on. Just reorganize them, make sure that everything's easy to access and you can see what you need. You also want to go through the low voltage fuse signs, just make sure they're all there. Sometimes they have a habit of flying off the back of the MUS. And also just to go over a couple spare fuses, your SMU5s, is just to make sure that everything's still there, all the bolts are on it, and bring them out if there's a fuse inside of them.